go. Stretch it out a little bit. Okay, so today, Friday the 13th, we'll do a little review. And then you'll have spring break to get ready for the exam. The Friday you can come back. Okay, so as always, I defer to the class for any specific problems you're having before I start talking. I want to be sure and get everybody's concerns covered before I start throwing stuff up here. Anything in particular bothering you? Homework problems? Any one of those that's sticking in your craw?
Maybe touch on last week's stuff.
Last week? Okay. Let's see. Right. Is that what everybody else wants? Or do you need to look at chapters 4 and 5? Anything in 4 and 5? Okay. Okay. So we'll get to 6 in a minute. Okay. So the chapter 4 and 5 deal with chemical bonding. And in addition, well, as a consequence, nomenclature, that's how do you name compounds. So we need two things. We need rules and we need the periodic table to tell us about charges. Okay, so let's look at the periodic table for a second. The way the table is structured, which unfortunately our viewers don't get to see, maybe I can sort of rough it out here. Okay, so you got the periodic table. That. And we get maybe 2 periods here, and then this one goes all the way across here. Like that. And then we got a couple down here. Okay. All right. Generally speaking, these, actually there are 2 here. Yep, there are 2 here. 2 groups on this side. These are the alkali metals, and this doesn't include hydrogens. Hydrogens up there, helium's up here. Okay, so the alkali metals are +1 charge. Always. Alkaline earths are always +2s. The ones with boron and aluminum down to about right there. Gallium. Oops. And probably indium too. These are all +3s. Charge. Fixed. Right? So when we're naming compounds, we're using a binary model. That is, you have a plus is the first one and a negative is the second one. Cation first, anion second in the compound. And we need to know which ones of the metals are fixed charge. those are the only ones that are fixed of the metals, as far as we're concerned. There are a couple down here, but I'll sort of set those aside for the variable charge, just so that we don't get too confused. Then over here we have the noble gases. They're always 0 charge, but they don't bond with anybody. Then we have the halogens. They're -1s. Then we have the chalcogens, -2s. So oxygens, and the fluorine and its neighbors, its family. Oxygen and its family, -2. And then nitrogen, -3. And then when we get to carbon, if it's part of if it's a carbide, if carbon's in the second position, then it's -4. But if it's in the first position, that usually means that it's a type 3 compound, non-metal, non-metal. If it's in the second position, there'll be a metal first, then the carbon. In that case, the metal takes the positive charge, carbon has to be the negative charge. Okay. For those cases, rare cases where we have that. Okay, so these guys in here, the transition metals, these are all variable charge. And we have a special rule for those, for that group. And remember, the nonmetals go like that on down. And over here, the nonmetals are the negative charged ones, the metals are the positive charged ones. And this variable charge bleeds off down into here a little bit too, like for tin and lead, those metals. Okay, so now that we know where everything's located, we can talk about how to name the compounds using our convention. So the type 1s, 2s, and 3s. Type compounds. The type 1s and 2s are both metal, non-metal. Okay? Type 3s are non-metal, non-metal. Okay? So these are going to be named with the cation first. Just name the element. That's it. And then the cation, the anion, the negative one, you end it with IDE. Okay? So for instance, sodium comes from the alkali metals, chlorine from the halogens, so that's a -1 and +1. You only need one of each. Right? So this is going to be sodium chloride. And you can go backwards and forwards without any mistakes. There's no ambiguity in this method. Go the other direction. Say we have calcium and fluorine, right? Well, fluorine has to be a -1 charge, right? Calcium is from the alkaline earths, so it has to be a +2. That means we need 2 fluorines. So that's how you would write that one. And then you name it with our type 1 convention, just say calcium fluoride. That's it. You don't say anything about the charge. You don't have to say anything about how many there are, because this can only be that. Okay? Type 1. Type 2, the metal can be variable charge. Right? So we do have to say in the name, what is the charge on the metal? So for instance, iron and oxygen in that ratio. We know that oxygen has to be a -2 charge. So if there's only one iron, it has to be a +2 charge. There's just only one of them. right? So we would say iron, and then the charge, and then oxide. Okay? Now, if we have this compound, and I told you that iron was a +3 charge, and you know that oxygen is a -2, and the ratio has to be 2 irons and 3 oxygens, because 3 times 2 minus is 6 minus, and 2 times 3 plus is 6 plus. Yeah, cross multiply. And then naming it, you say iron 3 oxide, and you're done. That's all you need to know, and you can write this from that. Okay, and the last one, type 3 compounds, non-metal, non-metal. Right, so if both of the elements come from the non-metal side, they don't have charges. These are both ionic compounds. These are always covalent, so they don't have a charge. But we, for convenience, simplicity, and non-ambiguity, we model this one after that one. And we just say the first one, say that and that would be carbon. Since there's no charge, we have to say how many of each one there are. So this is 1 carbon. We never say mono in the first. And then dioxide. Okay. Or if it was just 1, you know, the deadly form, it would be carbon monoxide. Okay, so let's say we have this one. And it's complicated a little bit. Diphosphorus pentoxide. Okay, how would we write that one? Just have a 2 here. Like that, and you're done. Okay. So if you're faced with a choice that you have to make, so you're naming something, you're given the compound, then you look to see where do they come from. Is it a metal, non-metal, or a non-metal, non-metal? If it's a metal, non-metal, it's got to be one of these. If it's a non-metal, non-metal, you just go straight to this one. But if it's a metal, non-metal, then you have to ask yourself, is the metal a fixed charge or variable charge? And then you look at your periodic table. Where does it come from? Here, here, here. Then it's type 1. Use that convention. Any place else? Use type 2. So that's like your decision tree. Okay. Let's see. Oh, polyatomics. Right? If you have a polyatomic ion in there somewhere, polyatomic ions are always fixed charge. Right? Once you know the name of the polyatomic, you know how to write it and you know its charge. So if we say, and polyatomics always fit into one of these. You never have a polyatomic with this convention. It's always a 1 or a 2. Right? So if we have ammonium, which one would that be, the cation or the anion? I gave you a list of polyatomics, didn't I? Yeah, okay. And let me check to be sure, but that should be with these. Okay. All right. I'll tell you what. You have to put it in the exam. All right. If you're faced with a polyatomic, just ask me and I'll tell you what it is. Okay. But I usually put that list in the exam, so you don't have to guess. You just look it up. Okay, so this one is going to be, that's it. That's all it can be. It can't be anything else. Ammonium. So this is the cation. It would be the first one. And then you would combine it with an anion of some kind. Let's say if it's chloride, you would just say like that. Charges are balanced. You're done. Okay. Suppose we combined it with let's see. How about this one? Suppose there are two polyatomics together. Okay. Now we need to know what sulfate is. Sulfate is like that. Okay. So now you have to balance the charges. Right? So you need 2 pluses to balance that 2 minus, which means you need 2 ammoniums. But you can't change these subscripts. The only way to get 2 of them is with parentheses. Right? Because this polyatomic ions are actually, they're covalently bound with a charge that's spread over the entire mixture. So you can't change the subscripts, and the only way to get more than one of them is with parentheses. Okay. If we have something like this 3 plus, and then sulfate, how do you do that one? Mm-hmm. 2 over here, and 3 over there, like that. Now the name of this one would be our type 2 convention, iron 3. Sulfate. That's it. You got that name, you got the formula, vice versa. Okay. Oh, we did acids too, didn't we? Naming acids. We didn't do acids. Let me check to see. It would have been probably chapter 5. We may have just sort of glossed over it if we did anything. No, we didn't. Doesn't look like it, does it? What did you guys look out? We didn't, if we didn't do acids. Yeah, we look in chapter 4, just to be sure. Because if it's in here, we need to review it. Yeah, we did. Okay, acids. Let's see. I'll take this over here. Start back over on this side. So how do you know you have an acid? Well, if you have the name, it says acid, right? What if you just got the formula? How do you know if you got an acid? Starts with a hydrogen, doesn't it? Yeah. All acids have to have a proton, at least one proton, to dissociate. That's what makes the solution acidic when you put them in water. Right? So you're always going to have at least one of those, and then something else attached to it. It could be, occupies the positive side. It could be just an element like that. Right? So if this is a gas, then you would name it by our type 1 convention. Right? It would just be hydrogen chloride. Right? But as soon as you put it in water, it becomes an acid. Because when you put it in water, it gives up those protons. And that's what makes the acid, those protons. Okay, so at this point, now we need a way to name it as an acid. Okay, so the first thing you look for is oxygen. Does it have oxygen? If there's no oxygen, then you start the name with hydro. Okay? Then you look at the second part. If it's chloride, then the "ide" becomes an "ic." So hydrochloric. And then finish it off with acid. That's the same for all of you. You always finish it off with acid. Okay? So what if we have something, let me think of something with a here we go. If it has an oxygen in it, it's going to be a polyatomic. Right? So you look for the polyatomic name. So if it has oxygen in it, with oxygen, no hydro. You don't say hydro. You start with the part that has the oxygen in it. You look for what is it called. This ion is nitrate. And 8's become X. In this case, the "ide" becomes an "ic." In this case, 8 becomes an "ic." So you don't say hydro, you just say, instead of nitrate, nitric. Say nitric acid. Okay? So there's another one in this family that has oxygen in it. It has one less oxygen. Like that one. So what's this polyatomic ion? Instead of nitrate, it's nitrite. And nitrite, H's become X, I's become Us's. So you just say nitrous acid. Okay? So there's the first clue you look for is, does it have oxygen in it? Well, no, the first clue is there a proton? It needs to be at least one. Sometimes there are 2 or 3. But at least one is the first one in the formula. That's the one that dissociates, comes apart in water. There are examples where you have hydrogens in different parts of the molecule, right? Like acetic acid. Right? So you have these hydrogens here and that one there. This one comes apart. These guys are bound too tightly. They're part of the polyatomic acetate. Right? So if this is acetate, it has oxygen in it, right? So if we start with 8, we don't say hydro, but 8's become X, so we say acetic acid. Okay? 5% acetic acid is vinegar. Okay. So the first thing you look for is the hydrogen. Be sure that when you put it in water, you've got some protons floating around. Then you look for oxygen. There's no oxygen, start with hydro, and then you take the anion and convert it to hydrochloric or fluoric or bromic, whatever the case may be. If there is oxygen, then you look for the name of the polyatomic. And H become X with no hydro, and I's become Us's. Oh, here's one. See, I'll put it down here. How about this one? There's a polyatomic with no oxygen in it, right? So you start with hydro. Okay, then you look for what is that? Cn minus is the cyanide ion, right? So I's become X. Hydro cyanic acid. Okay? Don't drink that. Okay. Let's see. I want to be sure I've covered everything. Oh, I was going to show you a large family of acids. Okay, so let's make room. Let's see here. 9:30. I don't want to eat up any of our lab time today. Okay. So if you look at, if you got it with you or left at home, look at your polyatomic ion chart, and you'll see that some of the families are related by how many oxygens they have in them. One of those is chlorine and oxygen. I always start with the one that has 3. Right? So that ion is the chlorate ion. If we take away one of the oxygens, still has a -1 charge, it becomes chlorite ion. We can take away another one. But there are no more suffixes to account for a loss of an oxygen, so we use a prefix. We say, all right, if it's this one, we want to go even lower. Hypochlorite, like underneath, like hypodermic under the skin. This is under the chloride. And then we go the other direction, add 1 oxygen. Right? In this case, we need another prefix. That means above. Perchlorate ion. So you got this family of oxygen-containing halogen polyatomics. Now, you can form the same type of arrangement, just substitute bromine in there. It would be bromate, bromite, hypobromite, perbromite. Or you could substitute iodine in there. So it'd be iodate, iodite, hypoiodite, periodite. So if you understand the way these things are built and their names, I mean, memorize these 4, and you got 8 more already done. Just follow the same pattern. Now, if we add a hydrogen to each one, we're going to make an acid. And that, of course, assumes that you put it in water. Right? It's aqueous. All right, so now those charges are gone because we've neutralized them with 1 positive proton. Okay? Now, what do we call Well, this one becomes, since it's oxygen, we don't say hydro, right? H become X. Chloric acid. This one becomes chlorous acid. This one becomes hypochlorous acid. And this one is an ick right here, but it also has a per in it. So this one is perchloric acid. Okay. And just like before, you can do the same thing, just substitute bromine or iodine in there, and you got a whole other set of acids done. There are other families, but they're not as big as this one. Sulfur has a sulfate, sulfite, that's it. Let's see. Selenium does the same thing. Selenite, selenous. Phosphate. You do phosphate like that, so it can take 3 protons. And this is phosphoric. Okay. Or if we say this, what would that one be? Phosphate, phosphite. Phosphorus. Okay. Sulfate, sulfite does the same thing. Nitrate, nitrite. How about this one? So that'd be a 2- charge there. Plus 1 here, so they balance. CO3, carbonate, means carbonic acid. That's what you get when you drink pop. Carbonated beverages. Actually, carbonated beverages have this, some of that in it too. That's why you can drop a nail in Coca-Cola, come back in a week and it's gone. This converts it to ferric phosphate. Iron and phosphate together are very friendly, so they make a compound. Actually, it's not ferric, it's probably ferrous, so that it's soluble. Iron 3 phosphate is insoluble, iron 2 phosphate is soluble. So if the nail's gone, you don't see any sediment at the bottom. There you go. Okay, so we got our nomenclature done. How about, I noticed that we also talked about models. Like bonding models. And let's see, it's not in this one, it's in chapter 5. Geometries and polarities. Electronegativity. Remember the trends for electronegativity? Electronegativity increases from lower left to upper right. And the farther apart the cation and the anion are, the more ionic character they have. But even when you have 2 nonmetals together, you can still have some polarity. In other words, the electron density can be favored toward one more than the other. And that gives you a slight difference in, see, example. Let's see. carbon tetrachloride, hydroxyl fluid. Chlorine is more electronegative than carbon, right? So the individual bonds are like that. And that's our symbol for polarity. Right? So the bonds are polar in that direction. Or we could say, like this, slight negative charge. Not a full, just a slight. So that means the bond is polar. But how about the whole molecule? Right? This is a tetrahedron, it's symmetrical. Right? So these pulls are all balanced against one another. They're all pulling out like this equally in all directions. So the molecule as a whole is nonpolar because of the geometry. So in order to determine the polarity of a molecule, you need to know two things. Bond polarity for each of your bonds, and two, geometry. Okay. If we had, let's see, how about this one? Take their carbon again, and we got chlorine, 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 hydrogen. So carbon and hydrogen are almost the same. So there's really no polarity here, but you still have polarity there and there and there. So the overall polarity of the molecule is toward the chlorine side. This is chloroform. Right? So it is polar. These bonds are polar. That one's not. Geometry says it's polar because it's not symmetrical. Okay, so how do we know the three-dimensional structure of a molecule? Right? We need a model for that. So the overall model is called LEM. That doesn't mean lunar excursion module. That means localized electron model. That just says that when you have a molecule and its bonds, that the electron density is assigned to individual atoms. They're localized for the atom. Right? And within that, we have a subset called the VSEPR, right? Which means valence shell electron pair repulsion model. All right. So keep track of the times. We'll go till about 11. All right. So we got an hour and 15 minutes. All right. So to make a long story short, how do you use this? Well, what you need is your Lewis dot structure. Remember that one? Okay. You need to be able to draw the Lewis dot structure. So if we say, let me try to pick one that's easy to just look one up. How to do the Lewis dot structure. Let's try. Let's try this one. sulfur dioxide. Why did I name it sulfur dioxide? Because sulfur and oxygen are both nonmetals. So you just say how many there are. Sulfur dioxide. Okay, now how do we do the Lewis dot structure? First thing you do, you need to know how many valence electrons there are for each atom. And to tell that, you look at the periodic table, and sulfur is, count from the left, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. 6 valence electrons for sulfur. Oxygen's in the same family, so it has 6 times 2. Right? So 3 times 6 is 18. We have 18 valence electrons, and the valence electrons are the only ones you're concerned with because they're the ones that are involved in bonding. Core electrons, just forget about them. So now you have to set it up so that your the sulfur is in the center, and the oxygens are on each side. And you put 2 electrons here and 2 electrons there. That's what that line means. A bond is 2 electrons, right? So we got 2 of them. That means -4. We got 14 more electrons that have to be positioned. You put them from the outside, work your way in, right? So let's say if we got 2 here, then in order to have an octet on oxygen, you need 6 more, right? 2, 4, 6, 8, 10, 12. So we have 2 more electrons. Oxygen's already got an octet, so we put those other 2 moving in there. Okay? Now you try to make an octet for the other, right? Without destroying the octet of the ones you've already got, right? You could either move electrons from here to a bond, here to a bond, or here to a bond. So what would the utility be of moving this one to a bond, these 2? Nothing, right? You still 2, 4, 6, move it over there, you still got 2, 4, 6, right? So you need to move electrons from here into a bond to give access to the sulfur, right? So if we move these 2 over here to make a bond, that makes a double bond here, and that oxygen now has 2 unbonded pairs plus these 2 bonded pairs, and that one, oops, there. Now everybody's got an octet. Okay? So now what do we do with that to say about the geometry? Because this says the geometry is linear. But the VSEPR model says you have to count bond groups and lone pairs around the central atom. So we have 1, 2, 3. That counts as 1 in the VSEPR model. That counts as 1. That counts as 1. So we got 3. Right? So for 3 groups, what's the geometry? Trigonal planar. We try to get these groups as far away from each other as possible. And the best way to do that is to spread them out in a triangle. There are 3 of them, so triangle is your only option. And since 3 can only be distributed in the same plane, right? You can't have 2 over here and then 1 out here, right? That puts it too close to the other. So trigonal planar, 2 here, 1 here. So it looks like this. Right? Trigonal planar. And the bond angle here, theoretically, so what's the internal, all the internal angles of a triangle have to add up to 180, or is it 360? 360, right? All the way around 360, right? So this has to be 120, right? But it's going to be a little bit less than 120. Why is that? Because of that unbonded pair. They tend to balloon out, and they put pressure on these guys. So it'll be less than 120. But if the question is asked, just put 120, right? Unless the specific question is asked, is it equal to, greater than, or less than 120, something like that. Then you would know it's less than 120. That's trigonal planar. Okay, so if you do all this Lewis stuff, and now this is trigonal planar electronic geometry, right? What's the molecular geometry? You just cover up the lone pairs. So what does it look like now? Bent, or your book might say angular. Molecular geometry, okay? Same as water. Water's bent also. Oh, by the way, well, I'll put it up here. Okay, so if we have groups here, number of groups, and then we have the electronic geometry here. We'll just do that first. If you only have one group, it can't be anything but linear, right? One group means it's linear, so we'll leave that one out. If you have two groups, if you only have two groups, right? If we didn't have that one, the farthest apart those groups can get is linear, right? And what's the angle of the bond? Right? The angle of the bond over here would be 180 degrees. Okay? If you have three groups, we just did that one. Trigonal planar, and the angle would be 120 degrees. We have four groups. We did that one earlier. That's a tetrahedron. Now this one you just have to memorize. The bond angles inside a tetrahedron are 109.5 degrees. Okay. How about five? The best way to position five groups is three in a trigonal planar here, and then one here and one there. So if you look at just the top part, you got this trigonal base with a apex on it, a trigonal pyramid. Okay, but you got one down here too. So it would be trigonal bipyramidal. Okay. Now let's see, what would that look like? Let's see. This, that. Got something in the middle, and we got one up here, one down here. So what are the bond angles? Well, if you take this bond angle, that's 180 degrees, right? What if you take this one to one of these? Right? That bond's right there to one of these, to one of these is 90 degrees. Right? Like that, and it's out here somewhere. That's 90 degrees. How about in here? You have something over here, right? What's the bond angle there? It's 120 degrees. Just like the trigonal planar, right? So you have three possible bond angles in trigonal bipyramidal. Okay? What if you have six? Well, six would put four around here and one up there and one down there, but that has a special name. It's called an octahedron. Right? So if you have an octahedron, you have 90 degrees here, 90 degrees here, and 180 degrees there. So 180 or 90 is your only possibility. Now that's all electronic geometry. If you have any lone pairs in there, you have to cover them up and see what's left over. Most of them are fairly straightforward. If you cover one up, you can figure it. Tetrahedron, if you cover up one lone pair, you got a trigonal pyramid. Cover up two, you got a bend. Trigonal bipyramidal gets a little tricky. How do you get these things as far apart as possible? Well, which one of these would you want to turn into a lone pair to make them as far apart as possible? I'm going to get rid of one of these on the trigonal, because it keeps this one and that one still far apart, and these guys are as far as you can get them. So what does that give you? Let's see. Turn it like this. It's a seesaw. So one lone pair in a trigonal bipyramidal is a seesaw. Two lone pairs, actually with two lone pairs, you get rid of, let's see, what would happen if you got rid of two? You got rid of these two here, like that one and that one, this one, this one. That would make a T. But if you got rid of these two, that would make a trigonal pyramid. So I don't know the answer to that one. So if I give you a question that looks like that one, then call me on it, and I'll just scratch it off. Because my intention is not to do that one. Okay, octahedron gets even more complex, so let's leave that away. We don't have time for it right now. So let's see, what do we do next? Let's see, bonding molecular. Okay, that takes care of chapters 4 and 5. Now we need 6. So 6 is chemical calculations, formulas, and balanced equations. All right. Or, in other words, equations in stoichiometry. Stoichiometry is a fancy way of saying what goes in must come out, and stoichiometry is how you keep track of everything. All right. So let's see, how did we attack this one first? Oh, molar masses. Right? When you have a formula, like say that, what is that, by the way? It's an acid, right? Okay, what's this polyatomic? Sulfate. Got an oxygen. Don't start with hydro. You just 8 become X. Sulfuric acid. Okay, what's the molar mass of sulfuric acid? All you have to do is add up the individual masses of each of the atoms. If you have 2 of them, hydrogen is 1.01 each. Right? Sulfur is 3206, one of them, and then oxygen is 16. And I always round off to 2 places. All right, so then we just multiply and add. So let's see, 2.02, back, 2.02 for hydrogen, 32.06 for sulfur, and 64 for oxygen. 9808. All right, so we got a number. What are the units? So
Well, it depends. Are you talking about individual atoms in one molecule? In which case, we're talking about atomic mass units. Okay? But if you're talking about a mole of these, right? 1 mole of these formulas, which equals 6.022 times 10 to the 23rd molecules, then we can say this is grams for one mole. Okay? This is 2.02 grams of hydrogen for every mole of those molecules, 32.06 grams of sulfur for each mole of those molecules, and 64 grams of oxygen for each mole. Okay? Now, since we're talking about concentration units here, or intensity factors, while we're here, what's the percentage by mass of each one of these in that molecule? Percentage by mass is just the ratio of this one to the whole, that one to the whole, that one to the whole, times 100. That's your percent. So if we want percent hydrogen, we just say 2.02 divided by 98.08 times 100. Okay. If we want to know how much oxygen is there, we just say 64 divided by the whole times 100. And this is percent hydrogen, this is percent oxygen. Okay? Let's see. Moving on. Now, if you want to find out notice, whenever you have a ratio like that, you have a conversion factor. Right? Because what does this say? It says for that molecule, 98 grams of it is equal to 1 mole. And when you have an equivalence, you got a conversion factor. This is just the conversion factor that's been reduced from that place to here. So if you have a certain mass of that compound and you want to know how many moles it has, you just say, okay, say we have 100 grams of sulfuric acid. 100 grams. Now, how do we convert that to moles? This is where you want to go. This is where you're coming from. Where you want to go goes on top. Where you're coming from goes on the bottom. Because numerator, denominator cancels. Numerator left over. Okay? So that means grams on the bottom, moles on the top. Here, grams on the top, moles on the bottom. You just flip it. Why can we do that? Because all conversion factors are equal to 1. The reciprocal of 1 is 1. Okay? You flip it, it's still 1. But now we've got the units where we want them. That cancels, leaves us with moles. So in your calculator now, you take this, divide it by that, that gives you the number of moles in 100 grams of sulfuric acid. Okay? Now, why do we need to know that? Well, in stoichiometry, when you have an equation, go right. Are we good?
What would you round that?
Round this too?
Yeah.
Conversion factors are lost the term. They don't count. This is the one that determines the answer. So you have 3. You have 3 significant figures. Exact, that's the term. This is an exact number. Right? So it doesn't matter. All conversion factors are exact numbers. Okay, so why do we need to be able to go backwards and forwards, grams to moles? Because of balanced equations. So let's say we have sulfuric acid. No, that's a bad example, because it's going to be in a solution. Let's take something else. Okay, let's go back to Haber-Bosch. We're going to combine nitrogen and hydrogen and make ammonia. Okay, so we need a 2 here, 2 nitrogens. And now we have 6 hydrogens, we need a 3 here. So that's balanced. How do we know it's balanced? 2 nitrogens, 2 nitrogens. 6 hydrogens, 6 hydrogens. We're good. Okay, so we need to know how to convert from mass to moles, because you can't go anywhere in that equation unless you're moles. You have to be numbers of something. Right? There's like a great wall here. There's another wall here. You can't get over that with mass. You can't get over it with anything except moles. Right? So if you got moles, you can go here, you can go there, or if you know this one, you can go back here, you can go back here, or if you know this one, you can go over there, or you can go over here. As long as you're moles, you can go anywhere you want to in that equation. Right? That's why you have to be able to convert. If the question says you have so many grams of this one, and you want to know how many grams of that one, right? If you have grams, so it's a different G than that. That's gas. This is grams. If you have so many grams of this one, then you got to make moles of this one. Then you can use your conversion factor, moles of nitrogen. So your nitrogen is going to be here, your ammonia is going to be here, and the conversion factor is coefficients. Right? 2 of these, 1 of those. So whatever moles you have here, you have, say, X moles here, you have 2X moles of ammonia here. If the question is the answers in moles, you're done. If it's in grams, now you got to convert that back. Moles on the bottom, grams on the top. So you need the molar mass of that compound. So many grams per mole, then you got grams. Okay, that's stoichiometry. Okay, so we balanced an equation, or I balanced an equation on the fly. I didn't use my budgeting procedure, and that's probably what you want to do, correct? We want to balance an equation or two. Because without a balanced equation, you're dead in the water. If you've got a reaction that needs to be described, and you want to do anything with it numerically, you have to have a balanced equation. There's no 2 ways about it. So, what if we do, how about, let's burn some gasoline, octane. And you would be given this, right? You don't know what octane is, right? So if the problem says burn octane in the atmosphere, right? If that's all it says, you're stuck, because you don't know what octane is and you don't know what it produces. You have to be given that. if this were general chemistry, I might say that's octane combined with oxygen in the air gives you something. And I would have already told them every time you burn a hydrocarbon in air, you get carbon dioxide and water. But for this class, I'd have to tell you everything. So we're going to take octane, combine it with oxygen in the air, which is diatomic, and it produces carbon dioxide and water. Okay? First thing, from the problem, you're given what are the reactants, what are the products. Now, it may only be in words. So if it says octane, and it gives you that one, of course, combined with oxygen gas, you have to know it's diatomic, yields carbon dioxide, you have to know how to write carbon dioxide, plus water. You know, water. You got to write those correctly first, or you're stuck. It'll never balance if you don't write them correctly. Okay, so once you get those positioned in reactant product, then we can go to our budget, right? So you count the elements, right? We have carbon, we have hydrogen, and we have oxygen. That's everybody. On this side, you have 8 carbons, you have 18 hydrogens, you have 2 oxygens. And on this side, you have 1 carbon, you have 2 hydrogens, and you have 1, 2, 3 oxygens. Okay? So what's the first trick? Look for elements by themselves. That element's right here by itself. Leave it alone. Don't do the oxygens first. Save them till last. So now we have to choose between carbon and hydrogen. Well, you don't know where to start at the top. You'll eventually get there. As long as you write these correctly and do your inventory, then it really doesn't matter where you start. It's just some starts make it easier than others, right? But you will get there. 8 carbons, we need 8 carbons. Remember, we only balance with coefficients. Once you write your compound, those subscripts are off limits. So 8 carbons takes care of the carbons, but it also affects the oxygens. That's 16, 17. Okay. Now we can do hydrogens. So we have 18 hydrogens here. Hydrogen's only one place here, so to get 18, we need 9 of them, right? Now that changed to oxygens again. So this is still 16 plus 9 is, what's that? 16 and 9 is 25, right? There we go. Now we can deal with oxygens on this side. Because they're only in one location, we can put a coefficient there that balances the equation. The problem is we've got an even and an odd. There's no whole number we can put in front of that oxygen that will give us 25 oxygens. We'll either get 24 or 26. Okay, so here's the next trick. Use a fraction. $25 halves gives you 25. Okay? Now, technically it's balanced, but it's not the way we want it. We want whole numbers only. Because who ever heard of, if you're talking about atoms and molecules, who ever heard of a half a molecule? Right? Now, if you're talking about moles, yeah, that you could get by with that. But we want whole numbers anyway. So how do you get rid of the fraction? Multiply by the denominator. Yeah. That would be a 2. Right? So the 2 comes in here. The 2 gets rid of here. So you're left with 25. 2 times 8 is 16, and 2 times 9 is 18. We were balanced before we did that. And if we multiply everything in the equation by the same number, we're still balanced. We would just have to multiply each one of these by 2. 2, 2. Still be the same ratio. We were already balanced. All we did was multiply the entire thing through by one number. We didn't change the ratios at all. So it's 2 octanes plus 25 oxygen molecules yields 16 carbon dioxide and 18 water. We're done. The only trick that I didn't show you in this one was polyatomic ions. If you have polyatomic ions in here, I don't know, like ammonium or sulfate or carbonate, right? Those, and they're on both sides, and they did not break apart in the process. In other words, you don't have ammonium on this side, and a nitrogen gas molecule on that side, right? If that's the case, you got to break them apart. But if the polyatomics are the same on both sides, and you don't have any destruction in the process, you can use the polyatomic as one of your budgeting items, okay? And that really simplifies things. Even if the polyatomic appears in one place here and two places over here, as long as it's intact, you can still use it. Okay. All right, so that's balanced equations. How are we doing on time? Okay, we're still okay, as long as I'm covering everything that I need to. Let's see. Okay, now we get to real stoichiometry. And yield. Those are the last two topics. So let's say we have, let's see, put it in the correct folder here. There we go. Let's say we have, let's check something first. And we did that one in class. Let's say okay. Let's say we have sodium chloride was aqueous aqueous solution, right? We have sodium chloride solution, and we're going to combine it with silver nitrate solution. Okay. What are we going to get? Well, since we haven't talked about precipitations, I'll tell you what you get. Double replacement. Silver and the sodium swap places, just like that. So silver combines with chlorine, and it precipitates, makes a solid. You put them together, you see this white, it's opaque, it's white stuff in there, and over time it just settles out. And the sodium and the nitrate combine, but they're soluble, so they stay in solution. Okay, so there's our equation. We just need to see if it's balanced. And I think it is balanced already, right? Because you have 1 plus, 1 minus, 1 plus, 1 minus, plus, minus, plus, minus. We have 1 sodium, 1 chloride, 1 silver, 1 nitrate. So we don't have to balance this one. But let's say we have, you're given let's say somebody did the calculations for you already, and you've got 21.3 grams of that in our container. And you have plenty of this. You're not going to run out of that, right? So the reaction will go to completion. You'll use up all of that, okay? How much silver chloride are you going to filter out on the bottom? How much will it produce? Mass. So we want to know how many grams of silver chloride will be produced from that reaction. Okay? Can you go from here to here directly? No. Balanced equations only work for numbers, moles. So you got to convert this one to moles before you can go anywhere in that equation. Right? So how do we convert grams to moles of silver nitrate? Molar mass. Right? Grams and moles. When you hear grams and moles together in the same phrase, think molar mass. Grams on the bottom, moles on the top, right? Because grams cancel grams, leaves you with moles. We just need a molar mass for silver nitrate. Okay, so now we have to go to the periodic table. And silver is 107.87. 107.87 silver. Nitrogen is 14.01. And 3 oxygens. What's 3 times 16? 48. Is that right? 2 16ths is 32. 32 plus 16, 48. Okay, so we add them together. 8, 12, 19, 25, 6. So if I did my math right, the molar mass of silver nitrate is 169.88 grams for each mole of that compound. Right? So now we just need 169.88 here, divided into 21.3. Okay, I got, let's see, in standard notation, 0.1254. Let's just say that. Grams of silver nitrate. Okay. Now, when we're doing problems like this, it's okay to keep more decimals than you're allowed here, right? Just so that as we do our calculations, we don't introduce rounding errors. All right, so now we can go, oh, excuse me, that's not grams. Somebody should have said something. That was moles. That's moles of silver nitrate, right? Cancel the grams, leave us with moles. Okay, now we can go, since we have moles of this, we can go to moles of that. So, you can do it the longhand way. Silver nitrate. What's our conversion factor? From silver nitrate to silver chloride. And that's really moles and moles. It's 1 to 1, isn't it? So that's how many moles of silver chloride we have. 1 to 1, got the same number of moles. Now, if we want to know the mass of silver chloride, we can just convert this to grams, right? How do you do that? Well, you want to cancel the moles and leave you with grams. There are again, grams and moles, molar mass. Only this time it's a different molar mass because we're talking about silver chloride. So that's silver, we already got that one. What's chlorine? I already know what it is because I've done this so many times. Can't see that far? Okay. It's 35, 45. Right. That's 2. 1 and 12 is 13. 1 and 12 is 13 for 143.32 grams per mole. There we go. So you just multiply that times our 0.1254. 143.2. And I get 17.9698. Now you can round, right, to 3 places. So round this to 3 places. You look at, here's the 3rd place. What's over here? 6. So that's bigger than 5, which means this is rounded to 10, which puts a 1 over here. So it's 18.0 grams of silver chloride. Okay? That's stoichiometry. We started off with something over here. We found out how much over there. That's known as the stoichiometric amount. That means that every last gram of this is converted to that 100%. All right, suppose you're not that good in the lab, right? And you spill some on the way. Okay? So there's an efficiency. There's a theoretical amount, which is that, and then there's an actual amount, which is what you actually get. And that gives you a percent yield. Right? So you have the actual amount that you isolated from this experiment, and then the theoretical amount that we just calculated. Okay? All right, suppose you were really sloppy, right? Say you only came up with 9 grams. You should have had 18 grams. Last time's 100. All right. So what's your percent yield? 50%. Okay. Now I think that's probably as in-depth as this class is going to go with percent yield. You can take percent yield and work backwards, right? If you say, okay, I want 18 grams of silver chloride, but I know my method has proven over time that I'm only good at 50% yield. Right? So you say, what do I need at 50% yield to give me 18 grams? Well, you need double that. You need 36 grams of theoretical yield. So 36 grams here translates into something over here, which would actually be double because they're 1 to 1. So it'd be 42.6 grams. You need to start off with 42 grams of this to actually give you 18 grams with that kind of yield. But I'm not going to explain that one. Just know how to calculate theoretical yield. Okay, is there anything I missed in this discussion? We didn't talk about limiting reactants, did we? Limiting reactants, I'm looking. That's the only other possibility in stoichiometry. No, I don't think we do. So what we're saying is, at this level, one of them is going to be excess, so that you don't run out. Right? The idea of a limiting reactant is if you have two absolute amounts, like grams of this and grams of that, one of them's going to run out. So you have to figure out which one runs out, and that determines the theoretical yield. That determines the stoichiometry of the reaction. Because once it runs out, reaction's done. Right? Even if you have some extra of the other one, it doesn't matter. Because it can't react with nothing. That's a double negative. Sorry. But we didn't get there in this class. That's just in case anybody ever springs it on you. You won't have a dumb stare in the face. Okay, any questions or comments or specific homework problems that you want to go over before we go in the lab? Well, let's see. We gave ourselves some fun. We finished early. So we got plenty of time to do our lab, it appears. Back in their proper place. That'll give you a whole next week to study for the exam. And let's see, are we going to have a lab when we come back? I don't think we did, but let me check.
I think this was last. I wasn't here.
Okay. You too? Okay. When we come back on the 27th, there's no lab. We'll have a lab the week after that. So when we come back, we'll have an exam, and then we'll jump into chapter 7. And that'll be it for that day. Okay. So we need connecting signs. Oh. Anybody else? Anybody else good? So we need 2 copies. All right. So what are we going to do in this one today? Let's see if we need any preliminaries before we go in there. How do we know a chemical reaction has occurred? Chemical change. There are some indicators. They're not infallible, but they're a good way to go. What are some ways that we know a chemical change has occurred?
Color.
Huh? Temperature? Is that what you say?
Yeah.
Go. Okay. Temperature. Either it gets cold or it gets warm. Okay. What else? Think of human senses. That's tactile. Huh? Smell. Okay. Yeah. Smell. Odor. Okay. An odor change, actually. Because some compounds stink by themselves, like sulfur dioxide. Anything else? Temperature, odor, let's see. Temperature, odor. How about the visual? What kind of visuals do you see? Sorry?
A change in color.
Color, okay, yeah. Color. Humans are visual creatures, so there are several visuals that come to mind. How about bubbles, gas? Okay. Oh, we looked at one just a little bit ago. Abbreviated precipitation, a solid form. Is that the one you were getting at?
No, I was gonna say gas.
Oh,
I was
okay,
getting that actually.
okay. Let's see, what else could possibly be that? Those are the only ones. Let's see, what else have we not? What other senses have we not? Oh, is there anything that you can hear from a reaction?
Coughing.
Yeah. Different types of sounds may come up. If it's a really huge sound, you're in trouble, right? Explosions. But if it's like a fizzing, that goes along with the visual. Let's see. One. Ooh, are we going to taste it? Sometimes odors are accompanied with a taste. Now, how do you smell something safely? It's called wafting, yeah. So you just, like this, so you just get a little bit of it. Tasting, they don't let us taste chemicals anymore. We used to taste for acids and bases. Acids are sour and bases are bitter. Not anymore. Let's see, that's 1, 2, 3, 4, 5. That's it, right? No more senses. Extrasensory perception. Feel the reactions occur. That doesn't work. Okay, so those are some of the signs that we're looking for in the lab today. So when you describe what's happening, you want to keep those in mind. And there are several things. This is kind of a qualitative lab where you're just mixing stuff together and you don't actually have to weigh anything. Just
So let's see, I'll just need to bring my copies in. That's all we'll need. So you can take a break and we'll reconvene in the lab. I still have to pull things out of the box, so don't be in a big hurry. Let's see.